Hello friends, in last lecture we finished the lectures at the point where we studied the theory of Hartung governor. Now we will start this lecture with a problem based on Hartung governor. So let's consider this problem. A spring controlled governor of Hartung type. The length of the ball and sleeve arms are 80 mm and 120 mm respectively. The total travel of sleeve is 25 mm. In the mid position, each spring is compressed by 50 mm and the radius of rotation of the mass center is 140 mm. Okay. Each ball has a mass of 4 kg and the spring has a stiffness of 10 kilonewton per meter of compression. The equivalent mass of the governor gear at the sleeve is 16 kg. Neglecting the movement due to the revolving masses when the arms are inclined, determine the ratio of the range of the speed and the mean speed of the governor. Also find the speed in the mid position. Okay, so here we have to find the ratio of the range of speed to the mean speed of the governor and speed of governor in the mid position. So first we will write the given data of problem. Okay, so here we'll write the given data. Now here the sleeve arm and ball arm are these. So ball arm is X, that is 120 mm. Sleeve arm is Y, which is 80 mm. Okay. Total travel of sleeve, that is total sleeve displacement from the minimum to the maximum position, is H, 25 mm. In the mid position, each spring is compressed by this. The initial compression of a spring is 50 mm and the mass, the radiation of rotation of the ball at the mean are say 140 mm. Mass of ball are 4 kg. The weight on the sleeve, that is mass on sleeve, total is 16 kg. Okay, so these are the data given in the problem. Consider this, 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 initial compression, this, stiffness of spring, small s is 10 kilonewton per, so the stiffness is given as 10 kilonewton per meter. Now, first of all, we will determine the mean speed of the governor because the mean radius is given here and it is easy to determine the mean speed, that is the speed of governor when the balls are in their mid position or sleeve is at the mid position. Okay, the sleeve is in mid position, so the configuration diagram for the mid position is, so in this figure, see the configuration of the system when the sleeve is in its mid position. You can see here in the mid position there is a centrifugal force Fc. Fc equals to mass of sleeve into mean speed square into mean radius. Okay, these are the configurations. The initial spring force is stiffness of a spring into the initial compression of a spring, I denote this initial compression by IC into the IC, that is initial compression of a spring, and determine this stiffness is 10 and initial compression is 0.05 meters. Okay, 10 into 0.05, that is 0.5 kilonewton, so 500 Newton. Okay, we don't know the value of mean speed and we have to determine the value of mean speed. That is this omega we have to calculate. Omega we have to calculate. Okay, we know that the value of mass m, we know that the value of r is 140 mm. So you can write the Fc in terms of omega. Okay, now we also know that the total mass on the sleeve is 16 kg. So its half is 8 kg. So value of m is here directly 16. We will substitute because this 2 is already here. Now the forces on sleeve is given by this. You can write a equilibrium equation, that is the movement of summation of movement of all forces about this point O equal to 0, which is equal to Fc into its distance x. Fc into x is equals to clockwise movements, that is x into x, and plus mg by 2 into y. By substituting these values, that is s, mg by 2, y, x, we can find the value of Fc from this relation, and finally Fc is equals to s plus mg by 2 into y by x. On substituting all the values here, and also replacing the value Fc as m omega square r is equals to s plus mg by 2 into y by x. So omega square is equals to 1 by small m into r s plus small s, not a small s, capital S, that is the spring force in the mean condition, is mg by 2 to y by x, and calculating after substitution we get the omega value as 33.2 radians per second. The value of n, that is rpm corresponding this omega value, is 317.0. So this is our first answer to this problem. The first last required thing, that's the speed at the mid position, is this. Now we will determine the sleeve displacement when governor configuration changes from mean position to the minimum speed position, and then sleeve lift or change in the configuration from mean speed to the highest speed position. Now I will show you configurations. So in this figure, again you can see the minimum position configuration and then maximum position configuration. This is for the minimum position and this is for the maximum position. Okay, here you can see the sleeve, the balls moves inward, that is towards the axis of governor, and here the balls moves in outward direction, that is the away from the axis of governor. Now in both the cases the configurations are same. this horizontal displacement here is denoted by A1. The displacement of sleeve is denoted by H1. Here the displacement of sleeve is denoted by H2, and displacement of ball due to the centrifugal force in outward radial direction is denoted by A2. We can easily write the relation between A1, R1, H1 as we know that R minus R1 divided by H1 is equals to X1 by Y1 or X by X1. Now similarly for here we can write, and using H1 and H2 we can determine the R1 and R2 values. Now what is the H1 and H2? Now since the sleeve will be in mid position, we assume the sleeve is in mid position in this configuration, for which the vertical arm is vertical, that is parallel to the governor axis, and horizontal arm is perpendicular to the governor axis, that is horizontal simply. Now if this is the mid position configuration, so definitely the half sleeve lift we will get below this configuration, and remaining half sleeve movement or lift we will get when the speed increases from this configuration. So this is the H2 and this is the H1. So from this analysis we can write here that H1 equals to H2 is equals to half of total sleeve motion between the minimum to maximum positions. So this is the value of H1 and H2 for both the configuration. Now we will find the values of R1 and R2 using this configuration diagrams. Let's consider this configuration diagram separately in the next. Now for this configuration, we can write here that A1 by H1 A1 by H1 equals to X by Y. Since the variation is very small, so we will neglect the distances x1 and x2. So x1 is also approximately equal to the x here. Using this configuration, we can find the value of A1, or A1 is written as R minus R1 divided by H1 is equals to X by Y. So you can determine the value of R1 from this relation, because R is known 140 mm. By substituting the value, all the values, you can determine the value of R1 is 0.132 meters. So the value of R1. Now we can write the centrifugal force for this configuration. Fc1 is equals to m omega 1 square R1. Okay, here we don't know the value of omega 1. Now the spring force S is the value of a spring constant into the displacement of a spring, that is the initial compression minus this displacement, that is the A. Okay, the value of A1 here from here in R minus R1. So spring stiffness into initial compression minus R minus R1. Solving this relation, get value of S1 as spring force for this minimum speed configuration is 120 Newton. Value of S1. Value of, and the next is mg by 2 is as it is. This is 16 by 2 into g. Considering equilibrium, considering equilibrium of lever, we can write here that Fc1 into x1 approximately equal to x equals to s1 into x plus mg by 2 into y. So, and in this relation, we know that value of fc1 is in terms of omega 1, that is m omega 1 square s1, m omega 1 square, m omega 1 square r1, that is x equals to 420 newtons into x here, x plus mg. Mg is again the value of x is not substituted here, and also not substitute the value of s1 into x plus mg y by 2. So substituting the values of s1, mg, y, x, omega 1 square, r1, omega 1 can be calculated using this relation. Finally, if I substitute the values and calculate the value of omega 1, I get the value omega 1 is equals to 32 radians, and corresponding to value of omega 1, I get the value of n1 as 305.5 rpm. Similarly, for highest speed configuration which I have here, similarly for this next configuration, I will take this figure with me and take it with me on the next page where we are solving this problem. We'll paste it here, hide this particular portion. Now you can see here that the higher speed configuration here, we can write the value of A2, and the compression of the spring becomes initial compression plus this value A2. Okay, so here again Fc2 for this configuration is mass omega 2 square into r2. The spring force S2 is the stiffness of a spring into initial compression plus this A2, and A2 can be written as IC plus A2 can be written as the initial mean radius, not initial mean radius, R2, radius of maximum speed, minus initial mean radius R. So after substituting the values of small s, IC, that is initial compression, R and R2, you can determine the value of Fc2, and R2. For the value of R2, you can write the relation between R2 minus R1, R2 minus R divided by this displacement, which is H2, and it is equal to the H by 2 is equals to X by Y. Using this relation, you can find the value of R2, which is equals to 0.148 meters. Substituting value of R2 and R here, you can find the initial spring force in this next condition is 580 Newton. The value of Fc2 in terms of omega 2 square, by substituting the value of R2 here, you can find this value as 0.592 omega 2 square in newtons, and the value of capital M is same as usual. Writing the equilibrium equation, that is considering the movement about fulcrum point O. This is our fulcrum. We can write the equation like this: FC2 into X equals to S into S2 into X plus mg by 2 into Y. And solving this relation, we can find value of omega 2. Omega 2 is equals to 34.32 radians per second, and corresponding N2 value is P27.7 RPM. You can solve this by your own. So our previous case, the speed range is N2 minus N1, and this speed range comes as 22 RPM, and the ratio of speed range to the mean speed not mean speed, sorry, समझ आएंगे हम आपसे, speed range mean speed is, that is N2 minus N1 by mean speed. Mean speed is around 317 RPM. This is 22.7 by 317 equals to 0.07. It is basically 7%. In percentage, it is denoted as percentage 7%. Okay. So in this way, you can solve the problems based on the Hartung governors by drawing the configuration diagram. In problems of governors, the configuration diagrams are very important. You have to draw the configuration diagram for minimum speed. You have to draw the configuration diagram for the maximum speed. You have to draw the configuration diagram for the mean speed, and you can solve any type of problem using the geometry as well as the basic fundamental equilibrium equation. Okay. If you have any doubt or query related to these topics, you can send your doubts or queries on the numbers given below. Thank you.